Hey everyone, welcome to our presentation. We're going to be talking about how we built a one-click exploit targeting Messenger for Android. A quick word about our agenda for today. We're going to give you some background information before jumping into the actual exploitation. We'll then talk about the mitigations we took to prevent such future exploits in our applications, and then we'll hopefully leave some time at the end for questions. First, let us introduce ourselves. My name is Octavian, or Octav for short. I'm a product security engineer working for Meta in London. I'm currently working on Messenger and video calling security. I'm also a crypto enthusiast, and I have a computer science background.
Hello, everyone. My name is Andrew. I'm also on the product security team at Meta, working with Octavian. My current focus is on our family of app security with an emphasis on Messenger. My background is in vulnerability research, reverse engineering, and computer science.
And I am Ryan. I work in the offensive security group, and I mainly focus on the third-party apps and hardware that Meta relies on. Thanks.
Let's talk about defense through offense. DTO is an internal exploit exercise at Meta. When we find a vulnerability, our top priority is to first fix it and learn any other mitigation and prevention outcomes. Then we note down the most interesting and exploitable vulnerabilities. At a later time, when we gather enough vulnerabilities to hopefully be able to exploit a full chain RCE, we get down to work. And to do so, we internally reintroduce the vulnerabilities into the latest version of our products, and then we set a plan for writing the exploit. There are numerous benefits of doing so. Through exploitation, we discover new weaknesses, we find new attack surface, and we build data points for in-the-wild exploitation detection. We then work together with product teams to address the resulting engineering tasks, and so far, this initiative started around 45 engineering work streams meant to harden Meta products. This is a visual representation of the steps we take in the execution of this project. We document already fixed and interesting vulnerabilities. We patch them back in our products. We write the full chain working exploits, and then we brainstorm onto the next steps. We did 3 such exercises so far. The first one targeted the Meta Quest 2, namely a privilege escalation exploit scenario where a third-party application could take over the entire headset. There's a blog post on our engineering blog about this one. Secondly, we worked on a Bluetooth proximity attack on the Ray-Ban Stories smart glasses. An attacker in proximity range could fully compromise the glasses on 0-click. And then lastly, the topic for today, we developed a one-click calling exploit on Messenger for Android. Quick background information about Messenger. It is a messaging application that originally started on open chats and which is currently moving to full end-to-end encrypted chats like WhatsApp. It can also do audio and video calling, and it can also be used in our VR headsets. For messaging, the app uses a powerful library called MSys. It is written in C for cross-platform compatibility. It is managing the messages databases, accounts, and all the message exchanges. With the application now moving to end-to-end encrypted chats as the default, it is also important that MSys performs client-side validations of the messages and media content, as these are no longer visible for the server. For object management, the app uses the MCF framework, which stands for Messenger Core Foundation. On Apple platforms, it is a layer over the Core Foundation. On non-Apple platforms, it is an in-house cross-platform implementation. All MCF objects inherit from a base class. They are reference counted, and they encode type-specific functionality, such as initializers and destructors. The image on the right shows an MCF data object, which is basically an arbitrary length buffer. Its type ID is a pointer to a vtable for its MCF runtime class that contains the relevant initialize and finalize function pointers. Moving on, let's briefly talk about Messenger calling architecture. There's 2 big parts behind the video call, the signaling stack and the media stack. The signaling stack managed by an internal library called RSys, and signaling messages are exchanged between clients through Meta's infrastructure and are used to manage the call state for things like starting a call, adding a new person, exchanging data messages, and ending the call. All messages sent over the signaling channel are serialized using the Thrift protocol. The media stack is a separate channel where all video and audio frames are flowing through. This uses the open source WebRTC protocol, and frames are usually sent peer-to-peer in a one-on-one call, but it can also be sent in what's called SFU mode in group calls. Spark AR is a JavaScript AR effect engine powering experiences across Meta products. In Spark, developers can write their own AR effects and upload them onto the store. Group calling AR effects can be enabled by one participant, and they will be automatically started for all the others in the call as well. This happens on 0 click. On top of that, since clients might need to communicate with each other in such effects, the multi-peer AR effect features allows developers to exchange messages in their effects. Side note that starting January 2025, Spark third-party AR effects will be deprecated. This is not a security outcome. However, it is relevant for our context as it reduces attack surface. OK, now that we're done with our introduction, let's get into the exploitation scenario. The scenario we worked with is a one-click calling exploit initiated by a malicious caller. We used Pixel 6a and Android 12 in our testing, but the exploit would have applied to the newest devices as well. There are two constraints. First, the attacker must be able to call their victim. So the victim must have previously accepted the message, or the attacker found a callability bypass. Secondly, the victim must answer the call. This is the one-click part. We will show you how we make this very likely to happen. Lastly, after call accept, if everything goes well, the attacker will gain code execution on the victim's phone. Our exploit chains primitives from a set of 4 vulnerabilities. These are a mix of issues crossing different family of apps components. All these vulnerabilities were internally discovered during code review and have been fully fixed. Let's talk about the first vulnerability. This one is in RSys, and it allows the attacker to spoof the incoming caller metadata such that the victim will see that the call is coming from someone else. The second vulnerability is an out-of-bounds read in one of the C++ methods used by the Spark AR effects, and this is what we used for an information disclosure and ASLR bypass. The third vulnerability allowed us to send signaling messages over the media data channel. Remember, these channels were separate. So by doing so, malicious calling clients can send signaling messages that were supposed to be only allowed for the server, thus bypassing some of the restrictions. And lastly, an incorrect signed integer comparison leads to an out-of-bound write in one of the C++ methods used in RSys on the signaling stack. We use this to override some objects on the heap in order to gain a code execution. This is a high-level overview of the full chain working exploit. We will detail all these steps going forward, but for now, we start the exploit by sending a shared library in an end-to-end encrypted chat. We call the victim, and at the same time, we spray the heap with certain objects. The victim answers the call. We enable the AR effect for all participants. We disclose memory contents and bypass ASLR. And then we trigger the out-of-bound write and gain control flow hijack. Let's talk about the first primitive. In end-to-end encrypted chats, file contents are encrypted, so the server cannot parse or understand them. We use this to send the shared library over to the victim's phone. Of course, we will need to know the path of where the file will be saved on the victim device, but luckily we can predict it since it uses a SHA-256 hash of the contents. Remember, we control the file, so we can predict the path. This is how it would look like. On the right-hand side, we send the file before starting the call. This can be even days before, and then we know the path at which the shared library will be saved on the victim's device. OK, let's talk about the second primitive related to spoofing the caller name and heap spraying. When someone starts a call, they send an initial join request on the signaling channel. The message is processed by the backend server, and it is turned into a ring request that then gets sent to the callee, which makes their phone start ringing. Join requests contain some up messages used for setting the call up. They are reflected in what the callee receives in the ring request. They're basically a vector of topic and data pairs. However, one of these topics, named call metadata, allows the attacker to set data about the caller. This was intended to be used for server-side only, but the attackers could set it as well. Let's see how this looks like. So the attacker, in their patched client, would create a new data message and set the topic to call metadata. They would put the payload to contain the caller name, in this case, innocent caller, and the profile picture. Then they will pack this data message into the other app messages and serialize the whole thrift payload. They send it on the signaling channel. The victim client receives it, and because it detects the call metadata topic, it will run this piece of code, which basically changes the caller name and the profile picture. This is how we make sure that the victim is very likely to answer the call. We can use social engineering and other techniques to set the caller name and picture to someone familiar with the victim. Passing it to Ryan for the following slides.
Okay, so before I step into the next phase of our exploit, I want to take a brief detour to talk about the Scudo allocator. So Scudo has been the default heap allocator on Android since Android 11. So all the malloc and free calls are going through Scudo here. Scudo is meant to be a hardened allocator that implements several features to make heap-based exploitation more difficult. The first is a checksum over the heap chunk metadata that'll help detect corruption upon free. And then Scudo also separates allocations into size-based classes, where each class is allocated from a separate region in memory. This makes it so that allocations of different sizes aren't going to be adjacent to each other. And then there are also guard pages between each of the regions, which will catch linear overwriting that crosses region boundaries. And then finally, the order in which chunks are returned from Scudo is randomized so that there's less predictable layout between runs. And each of these mitigations are things we did have to work around to get our exploit working. So the memory corruption vulnerability that we eventually want to use to execute or hijack control flow is a relative out-of-bounds write. So we wanted to find some objects on the heap that we could target for overriding and control flow hijack. And it turns out that that same ring request message that we used for caller ID spoofing is also useful for this purpose. The ring request contains this app messages array, which is an array of data messages. And each data message gets deserialized into one of these MCF data objects. And the MCF data objects are very useful for heap spraying, as the attacker, or us in this case, has full control over the size and contents of the internal buffer portion, as well as the number of these objects that are allocated through the length of that messages array. So through one ring request message, we can trigger about 1 megabyte worth of MCF data allocations. And then each MCF data gets attached to a call context, which persists through the duration of the call. And then upon the termination of the call, each of the objects is freed. So we can target the type ID field in the MCF data, as this is essentially just a function table pointer. And as mentioned before, one of the functions in this function table is a finalized function that will be called from the MCF data destructor. So if we can overwrite the type ID in one of the MCF datas, we effectively have a control flow hijack. So during that call initiation, we want to spray the heap with those MCF datas. But as mentioned before, Scudo shuffles the chunks, but this chunk order randomization doesn't actually apply across the entire region. Chunks are allocated in Scudo in batches called transfer batches, and the chunks within each batch are shuffled, but then each subsequently allocated transfer batch is carved out of the class region in a linear fashion. So if you can trigger many allocations back to back, as we can with that array of MCF datas, we can essentially get a large contiguous area within the class region allocated with attacker-controlled data. So we targeted with our MCF data this hex 160 sized class region, as this is the region that our out-of-bounds write will be originating in. So this does give us a large target to aim for when we do eventually trigger our memory corruption. So up to this point, we've sprayed the heap during the call initiation. And this is before the victim answers the call. So the next thing we do need is for the victim to answer the call. And as soon as they answer the call, we can immediately enable a malicious Spark AR effect. And remember, the Spark AR effects are programmable interactive video calling effects that you can program using a JavaScript API. And we're able to enable that effect for all participants, even in a group call, giving us JavaScript execution on all participants' client. And then we use a vulnerability within the JavaScript API to disclose some memory contents for our ASLR bypass. The vulnerable API we targeted is called getForeground%. GetForeground% accepts this signed integer mask ID parameter. And then that mask ID is used to directly index into a standard C++ vector. So this gives us a out-of-bounds read. And this is easily triggered directly from the Spark AR JavaScript, as we show here, where we just create an instance of the class and access that foreground% property. The value that we get back from this out-of-bounds read is in the form of a 32-bit float. And what we're going to eventually want to do with this is read some pointers off the heap. But we can just combine two adjacent 32-bit reads to get the 64-bit values. Because it is a 32-bit floating point, not every arbitrary memory value we attempt to read actually results in a valid float. So there are some indexes with this out-of-bounds read that are unreadable. In practice, this isn't much of an issue, as all of the pointer values we do want to find turn out to cast properly to floats. Okay, so now that we have a 64-bit relative out-of-bounds read, we can probably get this to work for disclosing enough info to bypass ASLR, but we really don't know that much about the heap layout at this point. We still do know that the vector we're accessing out of bounds is 12 bytes in size, so it's in the smallest Guzu class region. And so we would like to turn this index-based relative read into an arbitrary read at any address, just to be a little more flexible. And to do this, or one way we can do this is figuring out the base address of that vector we're accessing. But how can we go about finding that base address? We started with this observation that there's quite a few objects on the heap that have pointers to themselves or self-referential pointers in them. Some things like this are linked lists or objects with internal buffers where the first member of that object is a pointer to its own buffer. And if we can find some of these objects on the heap, we can use the address we read along with the index we use to read it to figure out the base address of the vector. But in order to find these, we sequentially scan the heap, reading 64 bits at a time using that relative read, looking for things that look like pointers. So we applied several heuristics to determine if the red values are valid pointers. The first of which is looking for the pointer tags, which is the top byte being set to hex B4. And then we're really only interested in finding pointers that point to the beginning of a Scudo chunk. And all the Scudo chunks are 16-bit aligned, so we check each value for 16-bit alignment. And then the pointers typically have high entropy, so we compute the entropy over bits 4 through 39 of the pointer. And if it's got low entropy, we discard it as a non-interesting pointer for our purpose. So for each of these candidate pointers we find, we use the pointer value we read with the index we use to read it to calculate a candidate base address for that vector. Now this may or may not be the correct real base address for the vector. In the event that the pointer we read is actually a self-referential pointer, then this is the correct address. If the pointer we read is not actually a self-referential pointer, then this is the incorrect address. But in either case, we add the values to a frequency map. And then after reading a predetermined number of pointers off the heap, we just take the most commonly occurring candidate address from that table and treat that as our vector base address. And at least in the memory access patterns for our target app, this was a very reliable way of finding that base address. So now we've found that base address and we've turned our relative read into an arbitrary read so we can read from anywhere we choose. And we want to use this arbitrary read primitive to find a code pointer that we can use to start building our job chain. This is another place where the MCF data objects came in very handy. As, again, those MCF data objects start with a type ID pointer. And those type IDs always point into a library called libcoldstart. And libcoldstart contains all the gadgets that we need. But the problem is, so far we've only been reading relative to that vector in the smallest Scudo class region. And that class region is too small to contain any MCF data objects. So we need a safe way to find where some of the other Scudo classes exist. And to do this, we again use the same relative read for scanning pointers in the current class region. And for each pointer we find, we can follow it using the arbitrary read and read the chunk metadata associated with that pointer to figure out which Scudo class it belongs to. And by doing this, we're able to find pointers into most of the larger Scudo regions and begin to use those as a starting point to search for MCF data objects. So searching for the MCF data objects in the larger bins is pretty straightforward, as they have a very predictable structure. Each MCF data object starts with that type ID pointer. And the type ID pointers have a predictable alignment requirement, so we can discard anything that doesn't match that alignment requirement. And then there's also 2 reference count values in every object. So we can look at the offset for those reference counts and check if the values are within a reasonable range for reference counting. And then we add each object we find to a list. Once we found enough objects with the same type ID value, we can safely assume that that is the MCF data we're looking for, and use that type ID to find the base address of libcoldstart and start building our job chain. So while we can build our job chain, we still need to find a reliable place to put it. To do this, we just again use the Spark AR JavaScript to spray the heap with these uint8 arrays, filling them initially with a predictable pattern that we can then scan for using our arbitrary read. Once we've found one of the uint8 arrays, we can then fill it with our job chain payload. And the job chain payload contains both the gadget addresses as well as a fake MCF type ID, which contains the overwritten function pointers. And then once we've put our payload in place, we use another feature of the Spark AR API called multi-peer messaging, which just lets us send the address of the uint8 buffer from the victim client back to our malicious client, which then gives us everything we need to be ready to hijack control flow. And I'll let Andrew talk about that.
All right, so at this point, we've prepared our environment on the victim client. We've sent them a shared library, we've defeated ASLR, and we've prepared memory to have our job chain payload. So now we get to execute our control flow hijack. So to do this, we actually will use 2 vulnerabilities to combine them together to build our out-of-bounds write primitive. So the first vulnerability is actually sending signaling messages that are usually reserved for the server to send to clients. We're going to send those directly client to client. There are some constraints here on the amount of data that you can send, as well as how many times you can use this vulnerability per call. So we're using an RTP data channel, which caps the message amount at 1,024 bytes. And this is also 1 shot per call, because the minute we use this vulnerability, we're going to alter the state machine in an irreparable way. So the thrift signaling message payload that we're going to be using is this one that we've listed here, the session description update. And this is a thrift message, and it consists of a map of I32 thrift types to media description update structure. So the media description update structure has 3 strings in it. So we're going to use this thrift signaling message payload to reach an out-of-bounds write vulnerability, root cause to an incorrect signed integer comparison. So this is the snippet here, and you'll notice that the signed integer key from our session description update signaling message payload is used in this comparison operation against the media description update size, which is an STD vector, So we're incorrectly casting size t to int, allowing position to be negative and accessing the STD vector out of bounds in a backwards direction. So the actual data that we're going to write out of bounds is our STD strings from the media description update value from our signaling payload. And there's some nice convenient behavior for STD string construction, particularly when using short strings. So namely strings that are less than 0x18 bytes in size. These will be constructed in place with up to 0x16 bytes of data and the last byte reserved for the size of the compact string. So that's our primitive. So now how do we actually use this to go about hijacking control flow, and what are we going to corrupt? We're going to corrupt the sprayed MCF data objects from our primitive 2 from the ring request. So we've sized the MCF data objects such that they're allocated in the same Scudo region, 0x160, as the media description updates vector we're accessing out of bounds. So as a reminder, Scudo is non-deterministic, and the exploit is not 100% reliable, and the out-of-bounds write does not always succeed based on the behavior of the allocator. So what are we actually going to corrupt within the MCF data object? We're going to corrupt the type table pointer, this type ID field, and we're going to point it to the fake MCF runtime class from the object we allocated from our AR effect, which will contain the finalized function pointer that we've hijacked to contain our gadget address. And when the call is ended, the finalized function pointer will execute once the MCF data object we've corrupted has been released and destroyed. So this is the state of memory before the override occurs. So we have our STD vector of media description updates with our index base. We're going to select the negative index from our session description update payload. We selected this index based on some offline sampling of running our exploit multiple times to figure out a value that is most likely to succeed. And we're going to point that at one of these MCF data objects that we've sprayed, and we're going to perform the overwrite with our 3 short STD strings. So there is some behavior to consider with the overwrite. So we want to make sure that we're overwriting the MCF type ID pointer, but not the fields that will break execution. So imagine that we overwrite a reference count to something that's not equal to 1 or whatever it happens to be. And when the call is finalized, our object will not be freed and our function pointer will not be called. So we need to be careful with this. So within this overwrite, we're going to point the type ID field to, again, the fake MCF runtime class from the AR effect primitive. So now we're going to talk about the job chain. So the job chain, what it's going to do is it's going to DL open our shared library from primitive 1. So at the time of call end, we're going to call MCF release on our MCF data object that we've corrupted. The reference count will drop to 0, and we'll call the corrupted finalized function pointer, which contains our first gadget address. So what our gadgets are doing here is it's preparing the ARM64 ABI arguments to pass the DL open so that we can pass the file path to open. And at the time of this gadget executing, the X19 register points to the start of the overwritten MCF data object. And when we dereference it, we'll have the start of the fake MCF runtime class object from the AR effect, and we'll place that into the X8 register. Then we're going to load 2 values from that same fake MCF runtime class object into the X0 and X9 registers. The X0 register will contain the DL open path, and the X9 register will contain the next gadget to execute, which is just a stub to call DL open, also within the libcoldstart library. And then we will call DL open, and we will achieve RCE by loading our library. So what are we actually executing once we DL open this thing? So within the shared libraries initialization routines, we're going to put in a reverse shell. So this will just launch a reverse shell for us to access remotely as if we were the application. So we're going to go through a demo. So we're going to start the call. We're going to spoof the data such that we see that the incoming caller data is not who we expect. We're going to enable the AR effect, which is going to leak the data back to our malicious client. Also perform the out of bounds write afterwards. Then we're going to end the call. And then we'll go to our listener where we'll have a reverse shell. And we see that we're the application. So as running with the reverse shell as the application, we can access anything that the application can access on the remote device. All right, so now we're going to talk about the mitigations we created as a result of this exercise and the gaps that we've closed. So one of the key messages from this presentation is that exploitation can provide defensive insight and make it harder for people performing the same work. So we've identified 15 plus security engineering outcomes from this exercise, not only hardening Messenger, but also the family of apps as a whole. So we're going to go through 5 of them that we thought were interesting to note. So the first is that we're preventing direct DL opens of end-to-end encrypted file attachments, particularly from a direct file attachment path. And we're doing this by hooking DL open in-app. Next, we've deployed libc++ hardening mode, the fast version of this. And what this mitigation does is it hooks STL container accesses with compiler instrumentation that checks the bounds to make sure they're checks the access to make sure they're within bounds when they're accessed. So this would actually make vulnerabilities 2 and 4, the out-of-bounds read and the out-of-bounds write, unexploitable. Next, we've hardened our server-side infrastructure that processes signaling messages. In particular, we thought the heap spraying primitive that we used was far too flexible and unnecessary to support in such a way. So we've hardened our validation logic of these payloads to restrict the amount of MCF data objects that can be sprayed using this primitive. We're also exploring isolating the MCF types away from the platform heap into an isolated heap. So had this been in place when we created the exploit, it would have made exploitation a lot more difficult since we wouldn't have been able to reach them so easily relative to the STD vector, which is allocated in the platform heap. And lastly, we are deploying CFI iCall protection within Messenger for Android, and we're continuously closing gaps in this protection. And we're restricting jump-oriented programming attacks by making the MCF function pointer calls more restricted, which would prevent what we've done. So takeaways, I'll mention it again. Exploitation can be used as a defensive exercise to harden products. Doing this sort of work on your products as a product security team can lead you to insights that you wouldn't get just by reviewing code or theoretically assessing what exploitation of vulnerabilities. You can come up with new mitigations and hardening work streams for your products. And I want to remind everyone that all vulnerabilities in this talk have been fixed. No one is vulnerable today. And I also want to have a call out to our bug bounty program. If anybody's interested in participating, we offer monetary rewards up to $300,000 US. If you're interested in participating, come see us after the talk. We actually have some bug bounty coupons you can use for a bonus on any submissions you have. And I'll also call out that WhatsApp is in scope for Pwn to Own Ireland towards the end of this month. So if anybody's interested in performing WhatsApp research, that would be a good venue to demonstrate it. And I also want to thank Sampriti Panda, who helped us with this exercise. And with that, yeah, thanks everybody for listening, and we'll take any questions. Anybody else?